Hello and welcome back to the channel. Today we're diving into one of the fundamental building blocks of computer science and digital electronics, Boolean algebra. This mathematical system, developed by George Boole in the mid-1800s, forms the theoretical foundation for all digital circuits and logical reasoning in computers. Let's start with what Boolean algebra actually is. Boolean algebra is an algebraic structure that deals exclusively with binary variables. That's variables that can only take two values, 0 and 1. You can think of these as false and true, or off and on. This simplicity is what makes it so powerful for digital systems. The structure of Boolean algebra is defined as a complemented distributive lattice. Now, don't let that intimidate you. It's simply a set B with three operations. Plus sign, which represents the OR operation. A dot, which represents the AND operation. A prime symbol, which represents the NOT operation. Along with these operations, we have two special elements, 0 and 1. Now, let's explore the axioms. These are the fundamental rules that Boolean algebra must follow. For any elements A, B, and C in our Boolean set, we have several important laws. First, we have the identity laws. A plus 0 equals A. A dot 1 equals A. Think of 0 as the do-nothing element for OR operations, and 1 as the do-nothing element for AND operations. Next, the domination laws. A plus 1 equals 1. A dot 0 equals 0. Here, 1 dominates any OR operation, and 0 dominates any AND operation. The idempotent laws tell us A plus A equals A. A dot A equals A. This means that ORing or ANDing a variable with itself doesn't change its value. The complement laws are crucial. A plus A prime equals 1. A dot A prime equals 0. A prime represents the complement or negation of A. So a variable is ORed with its complement always gives true, and ANDed with its complement always gives false. The commutative laws state A plus B equals B plus A. A dot B equals B dot A. Order doesn't matter in Boolean operations. The associative laws tell us A plus the quantity B plus C equals the quantity A plus B plus C. A dot the quantity B dot C equals the quantity A dot B dot C. Grouping doesn't affect the result. Finally, the distributive laws. A dot the quantity B plus C equals A dot B plus A dot C. A plus the quantity B dot C equals the quantity A plus B times the quantity A plus C. Notice that the second distributive law is different from regular algebra. This is unique to Boolean algebra. One of the most elegant aspects of Boolean algebra is the duality principle. This principle states that every valid Boolean expression remains valid if we perform two swaps. Swap AND operations with OR operations. Swap zeros with ones. For example, if A plus 0 equals A is true, then by duality, A dot 1 equals A is also true. This principle saves us tremendous effort in proving theorems. Prove one form, and you get the dual form for free. A Boolean function of n variables is a mapping from n tuple of binary values to a single binary value. Mathematically, we write this as f mapping from the set 0, 1 to the power of n to the set 0, 1. Here's something that might surprise you. The number of possible Boolean functions with n variables is 2 to the power of 2 to the power of n. For just 3 variables, that's 2 to the 8th power, which equals 256 different functions. This grows incredibly fast. When we design digital circuits, we often need standard forms for Boolean expressions. We have two main canonical forms. Sum of products, SOP. In sum of products form, we and variables together to form what we call minterms, then OR these minterms together. For example, f equals A dot B plus A prime dot C. This form is particularly useful for straightforward circuit implementation using AND/OR logic gates. Product of sums, POS. In product of sums form, we OR variables together to form max terms, then AND these max terms together. For example, f equals the quantity a plus b times the quantity a prime plus c. Let me clarify these important concepts. A minterm is a product, that's an operation, of all variables in either their true or complemented form. Each minterm yields 1 for exactly one input combination. A maxterm is a sum, that's an OR operation, of all variables in either their true or complemented form. Each maxterm yields 0 for exactly one input combination. Let's work through a practical example of Boolean simplification. Suppose we have f equals a dot b plus a dot b prime. Using the distributive law, we can factor out a. F equals a dot the quantity b plus b prime. Now, b plus b prime equals 1 by the complement law, so f equals a dot 1, which equals a by the identity law. So our original complex expression simplifies to just a. This kind of simplification is crucial for efficient circuit design. Karnaugh maps or K-maps are a graphical method for simplifying Boolean functions with up to 4 or 5 variables. Think of them as a visual way to apply Boolean algebra rules. The key rules for K-maps are: each group must contain a power of 2 cells, 1, 2, 4, 8, and so on. Groups should be as large as possible. All ones must be covered for SOP form, or all zeros for POS form. K-maps help us visualize adjacencies and identify which variables can be eliminated through Boolean laws. For functions with more than 4 variables, K-maps become unwieldy. The Quinn-McCluskey method provides a systematic, algorithmic approach that can be easily programmed. The steps are: list all minterms in binary representation. Group them by the number of ones. Compare adjacent groups to combine expressions differing by only 1 bit. Repeat until you find prime implicants. Use a prime implicant chart to find the essential prime implicants. This method guarantees a minimal solution and scales to any number of variables. Let's discuss where Boolean algebra is applied in the real world. In digital circuit design, it's fundamental for designing and optimizing logic gates and circuits. In computer architecture, it's used in control units, arithmetic logic unit design, and memory addressing schemes. In software testing, Boolean expressions help create decision tables and analyze condition coverage. In database query optimization, logical expressions in SQL where clauses rely on Boolean principles. In artificial intelligence, logic-based rule systems and propositional reasoning use Boolean algebra extensively. Let's begin with prime numbers, the building blocks of all integers. A prime number is a natural number greater than 1 that has no positive divisors other than 1 and itself. The first few primes are 2, 3, 5, 7, 11, 13, 17, and so on. Here's an important fact. 2 is the only even prime number. Why? Because any other even number is divisible by 2, which violates the definition of a prime. The fundamental theorem of arithmetic tells us that any integer n greater than 1 can be uniquely represented, up to the ordering of factors, as a product of prime numbers. This is called prime factorization, and it's absolutely fundamental to number theory. Now, let's discuss the greatest common divisor, or GCD. The GCD of two integers a and b, denoted as GCD of a and b, is the largest positive integer that divides both a and b. The most efficient way to compute GCD is using the Euclidean algorithm. Here's how it works. GCD of a and b equals GCD of b and a modulo b. We repeat this process until b equals 0, at which point GCD of a and 0 equals a. Let me walk you through an example. GCD of 48 and 18. First step, GCD of 48 and 18 equals GCD of 18 and 48 mod 18, which is GCD of 18 and 12. Second step, GCD of 18 and 12 equals GCD of 12 and 18 mod 12, which is GCD of 12 and 6. Third step, GCD of 12 and 6 equals GCD of 6 and 12 mod 6, which is GCD of 6 and 0. Final step, GCD of 6 and 0 equals 6. So the GCD of 48 and 18 is 6. The least common multiple, or LCM, of two integers a and b is the smallest positive integer that is divisible by both a and b. There's a beautiful relationship between GCD and LCM. LCM of a and b equals a times b divided by GCD of a and b. Using our previous example, LCM of 48 and 18 equals 48 times 18 divided by 6, which equals 864 divided by 6, which equals 144. A recurrence relation is an equation that recursively defines a sequence where each term is defined as a function of its predecessors. The general form is a sub n equals f of a sub n minus 1, a sub n minus 2, up to a sub n minus k. Think of the Fibonacci sequence. Each term is the sum of the two preceding terms. That's a classic recurrence relation. Let's focus on first-order linear recurrence relations with constant coefficients. These have the form a sub n equals r times a sub n minus 1 plus c, where r and c are constants. To solve these, we need to consider two parts. The homogeneous part, when c equals 0. The particular solution, to handle the constant term. For the homogeneous part, if c equals 0, then a sub n equals r to the power n times a sub 0. For the general solution, we combine a sub n equals a times r to the power n plus a particular solution. Let me work through an example. A sub n equals 2 times a sub n minus 1 plus 3, with a sub 0 equals 1. First, solve the homogeneous part. A sub n homogeneous equals a times 2 to the power n. Next, find a particular solution. Let's try a constant. A sub n particular equals p. Substituting, p equals 2p plus 3. Solving, p minus 2p equals 3, so negative p equals 3. Therefore p equals negative 3. The total solution is a sub n equals a times 2 to the power n minus 3. Using the initial condition a sub 0 equals 1. 1 equals a times 2 to the power 0 minus 3. 1 equals a times 1 minus 3. 1 equals a minus 3. Therefore, a equals 4. So our final solution is a sub n equals 4 times 2 to the power n minus 3. Generating functions provide a powerful algebraic approach to sequence manipulation. A generating function encodes a sequence, a sub n, as a formal power series. G of x equals the sum from n equals 0 to infinity of a sub n times x to the power n. For example, if a sub n equals 1 for all n, then g of x equals the sum from n equals 0 to infinity of x to the power n, which equals 1 divided by 1 minus x, for absolute value of x less than 1. Generating functions allow us to translate recurrence relations into algebraic equations, making them easier to solve. Many fundamental algorithms follow a divide-and-conquer approach, leading to recurrence relations of the form t of n equals a times t of n divided by b plus f of n, where a is the number of subproblems. N divided by b is the size of each subproblem. F of n is the cost of combining results. Master's theorem provides a direct way to determine the time complexity of divide-and-conquer algorithms. For a recurrence of the form t of n equals a times t of n divided by b plus theta of n to the power d, we have three cases. Case 1. If d is less than log base b of a, then t of n equals theta of n to the power of log base b of a. Case 2. If d equals log base b of a, then t of n equals theta of n to the power of log base b of a times log n. Case 3. If d is greater than log base b of a, then t of n equals theta of n to the power d. Let me sketch the proof for case 1, where d is less than log base b of a. Starting with t of n equals a times t of n divided by b plus n to the power d. Expanding recursively, t of n equals a times t of n divided by b squared plus n divided by b to the power d, plus n to the power d. This equals a squared times t of n divided by b squared plus a times n divided by b to the power d plus n to the power d. At level I, the cost is a to the power I times n divided by b to the power I to the power d, which equals n to the power d times a divided by b to the power d to the power I. Let k equal log base b of n. After log base b of n steps, n divided by b to the power k equals 1. The total cost becomes a geometric series. N to the power d times the sum from I equals 0 to log base b of n of a divided by b to the power d to the power I. When a divided by b to the power d is greater than 1, this series grows exponentially and is dominated by its last term, giving us t of n equals theta of n to the power of log base b of a. Let's apply this to merge sort. T of n equals 2 times t of n divided by 2 plus theta of n. Here, a equals 2, b equals 2, d equals 1. So, log base b of a equals log base 2 of 2 equals 1. Since d equals log base b of a, we're in case 2. Therefore, t of n equals theta of n to the power 1 times log n, which equals theta of n log n. This confirms that merge sort has n log n time complexity. Today we've covered the mathematical foundations that underpin much of computer science. Remember, mathematics isn't just about getting the right answer, it's about understanding the elegant patterns and relationships that govern computational complexity. These tools will make you better problem solvers and more effective software engineers. That's a wrap. Thank you for watching this video. Don't forget to give it a like, share with your friends and subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.